Welcome to Sleepy Science Student, where we explore the cosmos one gentle breath at a time. Tonight, we're going on a slow, peaceful journey into something you experience every single moment, but probably never think about: the real movement of Earth through space. Not just the spinning and orbiting you learned about in school, but the genuine, intricate cosmic dance our planet performs as it travels through the Milky Way galaxy. I hope this video isn't too interesting, though if it does happen to keep you awake, at least you'll be learning something fascinating about your true address in the universe and the remarkable speeds at which you're traveling right now, even as you lie perfectly still. Not the worst way to spend a sleepless night. Before we drift among the stars together, I'd love it if you gave this video a like and maybe even subscribed if you haven't already. It really helps this curious little channel grow and means more sleepy students of the universe can find their way here. I'd also love to know where you're watching from and what time it is for you right now. Are you tuning in from a cozy bed in Stockholm at midnight, or listening from a hammock in Melbourne at noon while the summer sun filters through the trees? Let me know in the comments. It's always such a joy to see the sleepy science community scattered gently across the globe, all of us moving through space together in ways we're about to explore. Now, settle in. Get comfortable. You don't need to remember any of this. You don't need to take notes or stay alert. Just let the words wash over you like starlight falling softly through an open window. Let your shoulders relax. Slow your breathing down. And as we begin this gentle voyage into cosmic motion, remember, this video is for educational and relaxation purposes only. It's not intended as medical advice, navigational guidance for actual space travel, or an excuse for why you're late to work tomorrow because you're moving at 828,000 kilometers per hour through the galaxy. Ready? Let's begin. Let's talk about something curious. Right now, as you lie there in your bed or sit in your chair, you feel perfectly still. The world around you seems solid, fixed, unmoving. Your coffee cup sits quietly on the table. The walls stand motionless. Everything appears to be at rest. This feeling of stillness is one of the most convincing illusions in all of human experience. But here's the thing, and this is where our journey truly begins. You are not still. Not even remotely. You are, in fact, moving at speeds that would make even the fastest spacecraft humanity has ever built look like a leisurely afternoon stroll. You're spinning. You're orbiting. You're drifting through the solar system. You're sweeping through the galaxy. And you're doing all of this simultaneously, in a choreographed cosmic ballet that's been going on since before you were born, and will continue long after you're gone. The ancient Greeks believed Earth sat motionless at the center of everything. It made sense, didn't it? You couldn't feel any movement. Drop something, and it falls straight down, not at an angle as it would if the ground were rushing past beneath it. Birds fly just fine. Clouds drift lazily overhead. Nothing in everyday experience suggested the ground beneath their feet was moving at all, let alone hurtling through space at incomprehensible speeds. Then along came a few curious minds who looked a bit more carefully at the sky. Copernicus suggested, rather boldly for his time, that perhaps Earth orbited the Sun rather than the other way around. Galileo pointed his telescope upward and saw moons orbiting Jupiter. Tiny worlds that clearly weren't circling Earth. Slowly, gently, the illusion began to crack. We weren't the still center of everything. We were moving. But even those early astronomers, revolutionary as their ideas were, didn't grasp the full scope of Earth's motion. They understood rotation and orbital movement, which was remarkable enough. What they couldn't have known, what we've only really understood for about a century, is that our entire solar system is itself in motion, sweeping through the Milky Way galaxy at speeds that make Earth's orbit around the Sun look almost leisurely by comparison. You might think of Earth as having an address, like a house on a street, but your cosmic address is far more dynamic than any street number. It's more like coordinates on a ship that's sailing across an ocean, while that ocean itself flows around a planet. while that planet orbits a star, while that star, well, you get the idea. Motion, nested within motion, nested within motion, all the way up. Here's something to ponder as we settle deeper into this exploration. Every atom in your body, every cell, every molecule of air you breathe, is participating in this cosmic journey. The carbon in your bones formed in the heart of an ancient star and has been traveling through the galaxy ever since. You're not just on Earth. You're made of Earth. And Earth, as we're about to discover, is made of stardust that's been wandering the Milky Way for billions of years. The stillness you feel is real in its own way. Relative to the ground beneath you, you are indeed at rest. But zoom out just a bit. Pull back to see Earth from space, then the solar system, then the galaxy. And that stillness dissolves into the most elegant motion you could imagine. It's a bit like being on a train. Inside the car, you can walk normally, pour water, toss a ball. Everything behaves as if you're standing still. But look out the window, and you realize you're gliding past landscapes at tremendous speed. Scientists call this frame of reference, and it's one of the most important concepts in physics. Motion is always relative to something else. Relative to your bed, you're motionless. Relative to the sun, you're circling at about 30 kilometers per second. Relative to the center of the galaxy, you're moving at roughly 230 kilometers per second. None of these perspectives is more true than the others. They're just different ways of measuring the same cosmic dance. What we're going to explore together over the next few hours is exactly how Earth moves through space. Not the simplified version you learned in school. Earth spins, Earth orbits the sun, the end. But the complete, fascinating, multi-layered reality. We'll start with the movements you might already know about, and then, gently, we'll zoom out and out until we can see the full picture of our journey through the galaxy. And here's the beautiful part. Understanding this movement doesn't make the stillness you feel any less real. If anything, it makes it more precious. You're racing through the cosmos at speeds that defy imagination. And yet here you are, comfortable and safe, breathing slowly, feeling the gentle weight of gravity holding you down, experiencing the peace of a quiet moment. It's not just remarkable, it's quietly miraculous. So let's begin where most people think the story ends. Let's talk about the rotation of Earth, that daily spin that gives us sunrise and sunset, that makes the stars appear to wheel overhead, that shapes the weather and the oceans and the very length of our days. It's the first movement, the most familiar one, but as we'll discover, it's just the beginning of a much longer tale. Take a breath. Settle deeper. Let's spin gently into the first layer of Earth's cosmic motion. Earth rotates. You know this. Everyone knows this. But what does that actually mean? What does it feel like, physically, to be on a giant sphere that's turning once every 24 hours? And more curiously, why don't we feel it? Let's start with the basics, just to make sure we're all on the same page. Earth spins around an imaginary line called its axis, which runs from the North Pole to the South Pole. This axis is tilted about 23.5 degrees relative to Earth's orbital plane. We'll come back to why that matters later. But for now, just picture a tilted spinning top. That's Earth. One complete rotation takes approximately 24 hours, which we rather conveniently call a day. The speed of this rotation depends on where you are. At the equator, Earth's surface is moving at about 1,670 kilometers per hour, roughly 1,040 miles per hour if you prefer. That's faster than the speed of sound. You, right now, are potentially moving faster than a jet plane, just by lying there. As you move toward the poles, this speed decreases. At 45 degrees latitude, somewhere around the Great Lakes in North America or Bordeaux in France, you're moving at about 1,180 kilometers per hour. At the poles themselves, you're barely moving at all, just pirouetting slowly in place. But wait, you might wonder, if I'm moving at over 1,000 kilometers per hour, why don't I fly off into space? Why doesn't everything slide eastward? Why can birds fly in any direction they want without having to account for the ground rushing beneath them? The answer is gravity, working together with something called inertia. Gravity holds you to the surface with a force that's more than enough to overcome the centrifugal effect of Earth's rotation. You do weigh slightly less at the equator than at the poles because of this rotation, about 0.3% less, but it's nowhere near enough to make you float away. And as for everything moving together, well, the atmosphere rotates with Earth. The oceans rotate with Earth. Everything is moving together as a unit, which is why you don't notice it. It's a bit like being in a car traveling down a perfectly smooth highway at constant speed. You don't feel the motion unless the car accelerates, brakes, or turns. Earth's rotation is incredibly smooth and constant. Well, mostly constant, though we'll talk about the tiny variations later. So there's nothing to feel, no acceleration, no jerk, just steady, imperceptible spinning. Now here's where it gets interesting, at least if you're the sort of person who finds rotational dynamics interesting at bedtime, which I certainly hope you are. Earth's rotation isn't just about day and night, it shapes almost everything about our planet. The rotation causes something called the Coriolis effect, which makes moving objects appear to curve to the right in the northern hemisphere and to the left in the southern hemisphere. This effect shapes weather patterns, creating the spiraling hurricanes and cyclones you see in satellite images. It influences ocean currents. It even affects the way water drains from a sink, though that's more complicated and much more subtle than most people realize. The rotation creates something else too, a bulge. Earth isn't a perfect sphere. The centrifugal force of rotation causes the planet to bulge slightly at the equator and flatten a bit at the poles. The difference is small, only about 42 kilometers between the equatorial diameter and the polar diameter, but it's there. Earth is what scientists call an oblate spheroid. It's a lovely term, isn't it? Oblate spheroid. Let it roll around in your mind like a smooth pebble. Historically, humans took a long time to accept that Earth rotates. It seems obvious now, but put yourself in the sandals of an ancient astronomer. You look up and see the sun rise in the east, arc across the sky, and set in the west. The stars wheel overhead in great circles. The simplest explanation? The sky is rotating around a stationary Earth. It wasn't stupidity that led to this conclusion. It was perfectly reasonable inference based on available evidence. The first person we know of who seriously suggested Earth rotates was Aristarchus of Samos, way back in ancient Greece around 270 BCE. He also suggested Earth orbits the Sun, making him remarkably prescient, but his ideas didn't catch on. They seemed too wild, too contrary to obvious experience. Why would Earth be spinning if we couldn't feel it? And if it were spinning so fast, wouldn't everything fly off into space? It took until the 16th century for the idea to really gain traction, when Copernicus revived the heliocentric model. Even then, many educated people resisted. The Catholic Church famously opposed it, partly on theological grounds, and partly because it just seemed physically impossible. How could Earth be moving if everything felt still? The final proof came from an elegant experiment conducted by Léon Foucault in 1851. He hung a very long, heavy pendulum from the dome of the Pantheon in Paris and set it swinging. Over time, the plane of the pendulum's swing appeared to rotate. But it wasn't the pendulum rotating, it was Earth beneath it. The pendulum was simply continuing to swing in the same plane relative to the stars, while Earth turned underneath. It was beautiful, definitive, and visible proof that our planet spins. Nowadays, we can measure Earth's rotation with extraordinary precision. Atomic clocks can detect variations in the length of a day down to the microsecond. And here's something curious. Days are getting longer, very, very slowly, but measurably. About 1.7 milliseconds per century. The main culprit? The Moon. The Moon's gravity raises tides in Earth's oceans. These tides create friction, which very gradually slows Earth's rotation. At the same time, angular momentum is transferred to the Moon, causing it to slowly drift away from Earth at about 3.8 centimeters per year. It's a gentle cosmic trade-off. We spin a bit slower, and the Moon recedes a bit farther. In about 600 million years, Earth's day will be 25 hours long. But don't worry, you won't need to adjust your sleep schedule just yet. There's something almost meditative about Earth's rotation when you really think about it. This steady spin has been going on for about 4.5 billion years. When dinosaurs walked the Earth, they experienced slightly shorter days, perhaps 23 hours instead of 24. When the first simple cells emerged in ancient oceans, days might have been as short as 18 hours. And this spinning will continue, gradually slowing, for billions of years to come. Right now, as you lie there, you're partaking in this ancient motion. The same spin that brought dawn to ancient Egypt brings dawn to you. The same rotation that cooled the evening air for the first mammals now cools it for you. You're part of an unbroken chain of spinning days, stretching back to the very formation of our planet. The rotation is also why we have time zones, why jet lag exists, why the international dateline marks an arbitrary spot where today becomes tomorrow. It's why noon means the sun is highest in the sky wherever you are. It's why sundials work. So much of human civilization is built around this simple fact of rotation that we barely notice it anymore. But notice it now. Feel the stillness of the moment, and let yourself imagine, just lightly, just gently, that beneath that stillness, you're spinning. The ground is turning. The sky above holds its position while Earth wheels beneath it. You are on a cosmic carousel, and it never stops. Let's pause for a moment and breathe. The rotation is just the first movement, the most intimate one, the one that defines your days and nights. But Earth doesn't just spin, it also orbits, and that's where our journey gets even more interesting. Now we come to the movement most people learn about in school, Earth's orbit around the Sun. Once a year, every year, our planet completes a great elliptical loop through space, returning to approximately where it started, and then beginning again. This orbital motion is faster than most people realize, more complex than the simple diagrams suggest, and absolutely essential to life as we know it. Let's establish the basic facts first, softly and clearly. Earth orbits the Sun at an average distance of about 150 million kilometers. That's roughly 93 million miles. A distance so important in astronomy that it has its own name, 1 astronomical unit, or AU. Earth doesn't orbit in a perfect circle. The path is an ellipse, though not a very elongated one. At the closest approach, called perihelion, Earth is about 147 million kilometers from the Sun. At the farthest point, aphelion, it's about 152 million kilometers away. Curiously, perihelion occurs in early January, during Northern Hemisphere winter, while aphelion happens in early July, during Northern Hemisphere summer. This surprises people. Shouldn't we be warmer when we're closer to the Sun? But the distance variation is only about 3%, which isn't enough to overcome the effect of Earth's axial tilt. Seasons are caused by tilt, not by distance. When the Northern Hemisphere is tilted toward the Sun, it receives more direct sunlight and experiences summer, regardless of whether Earth is at perihelion or aphelion. The orbital speed is remarkable. Earth travels at an average velocity of about 30 kilometers per second around the Sun. That's roughly 107,000 kilometers per hour, or about 67,000 miles per hour. Every second, you move 30 kilometers through space. By the time you finish reading this sentence, you've traveled hundreds of kilometers along Earth's orbit, yet you feel nothing. No wind in your face, no sense of motion, just the quiet stillness of your room. The orbit takes 365.256 days to complete, not exactly 365, which is why we need leap years. Every 4 years we add an extra day to keep our calendar aligned with Earth's actual orbital period. Well, mostly every 4 years. The system is slightly more complex than that, with rules about century years, but we don't need to worry about those details right now. Let them drift away like leaves on a stream. What's truly elegant about Earth's orbit is that it's not chaotic or random. It's governed by gravity, specifically by the gravitational attraction between Earth and the Sun. Isaac Newton figured this out in the late 1600s, and his insight revolutionized our understanding of the cosmos. The Sun's gravity pulls Earth toward it, but Earth's forward motion keeps it from falling in. The result is a stable orbit, a constant falling around rather than falling into, a perpetual dance between gravitational attraction and inertial motion. You can think of it like swinging a ball on a string. The string provides an inward pull, like gravity. Your hand at the center is like the sun. The ball wants to fly off in a straight line due to inertia, but the string prevents that, causing it to circle instead. Earth is the ball. The sun's gravity is the string, and the orbit is the resulting circular path. Except, of course, that there's no actual string, and the orbit is an ellipse, not a circle. But the analogy holds up reasonably well for bedtime physics. The orbit of Earth is what gives us the year. Ancient cultures recognized that the sun's position against the background stars changes over time, that it moves through a band of constellations we now call the zodiac, returning to its starting position after about 365 days. They didn't know they were observing Earth's orbital motion from inside the orbit, but they tracked it carefully nonetheless, building calendars and planting crops, and marking time by the sun's annual journey across the sky. Here's something that might seem odd. When Earth is on one side of the sun, we see different constellations at night than when we're on the opposite side 6 months later. In January, the constellation Orion is prominent in the evening sky. By July, it's hidden behind the sun from our perspective, and we see different stars instead: Sagittarius, Scorpius, the summer constellations. The night sky is a calendar, slowly changing as Earth makes its orbital journey. The stars themselves barely move, but our viewing angle changes constantly. The orbit also creates something else, a phenomenon called stellar parallax. As Earth moves from one side of its orbit to the other, nearby stars appear to shift position slightly against the background of more distant stars. It's the same effect you notice when you close one eye and then the other. Objects at different distances appear to move. For centuries, astronomers looked for stellar parallax as proof that Earth really does orbit the sun, but the shifts are so tiny that they couldn't measure them until the 1830s, when Friedrich Bessel finally detected parallax in the star 61 Cygni in 1838. It was absolute confirmation that Earth indeed orbits the sun, and also provided the first measurement of the vast distances between stars. There's a beautiful symmetry to Earth's orbit. It happens at the same speed, in the same path, year after year after year. The orbit is so reliable that we can predict eclipses centuries in advance. We can calculate exactly where Earth will be on any future date. This predictability is what makes space travel possible. When we send a probe to Mars or Jupiter, we're essentially predicting where Earth and the target planet will be months or years in the future, then launching accordingly. But here's what's curious. Earth doesn't orbit around the sun. Not exactly. Both Earth and the sun orbit around their common center of mass, called the barycenter. For the Earth-Sun system, this barycenter is very close to the sun's center, actually inside the sun, because the sun is so much more massive than Earth. But it's not precisely at the sun's center. The sun itself makes a tiny wobble as Earth orbits, responding to Earth's gravitational pull. It's a mutual dance, not a one-sided circuit. This becomes more important when we consider the whole solar system. The sun doesn't sit perfectly still at the center. It wobbles in response to the combined gravitational pulls of all the planets, especially Jupiter, which is massive enough to shift the solar system's barycenter to just outside the sun's surface. The sun orbits this point even as the planets orbit the sun. Motion within motion, circles within circles, everything influencing everything else in a grand gravitational choreography. Let's take a moment here to appreciate what this means for you, personally. You're not just on Earth, you're orbiting the sun. Every memory you have, every experience, every moment of your life has occurred somewhere along this great elliptical path through space. When you were born, Earth was at one point in its orbit. Now, years later, you've circled the sun however many times you are years old. You've traveled literally trillions of kilometers through space, and you'll continue traveling until the day you die and beyond. The ancient Greeks had a beautiful word, cosmos, which meant not just the universe but also order and harmony. They believed the celestial spheres moved in perfect circles because circles represented perfection and divinity. We know now that the orbits are ellipses, not circles, and that they're governed by gravity rather than divine hands. But the harmony is still there. The order is still there. The cosmos still unfolds with elegant mathematical precision, as beautiful as anything those ancient philosophers imagined. As we drift deeper into our exploration of Earth's motion, remember that the orbit around the sun is still just one layer of the onion. Yes, you're spinning. Yes, you're orbiting. But the sun itself is not stationary, and that's where things begin to get truly cosmic in scale. Before we go there, though, let's talk about the solar system itself, not as individual planets on their lonely paths, but as a system moving together through the galaxy. Take another breath. Let the orbital motion settle into your mind. 30 kilometers per second, 107,000 kilometers per hour, circling, circling, circling for 4.5 billion years and counting. And now, gently, let's zoom out even further. The solar system is not just a collection of planets following their own independent paths. It's a family, bound together by gravity, moving as a unit through space. Every planet, every moon, every asteroid, every speck of dust in the solar system is part of this collective motion. And to understand how Earth moves through the galaxy, we first need to understand how the entire solar system behaves as a single system. Picture the solar system like a carousel at a fairground. Each planet is a horse or carriage on the carousel, moving in its own circular path. But the entire carousel itself is also moving. It's on a truck being driven down the highway. The planets orbit the sun, yes, but the sun itself is moving through the galaxy, dragging all of its planets along with it. The result is that the planets don't actually trace simple circles or ellipses in space. They trace helixes, spiral paths, like threads on a screw. Let's explore this idea more carefully, because it's not quite as simple as it first seems. When you see diagrams of the solar system in textbooks, they typically show the planets as if they're on a flat plane, all orbiting in neat circles or ellipses, with the sun at the center. This is accurate for understanding the relative positions of the planets from the sun's perspective. But it's deeply misleading if you want to understand what the planet's actual paths through space look like. The sun is moving through the galaxy at about 230 kilometers per second. That's roughly 828,000 kilometers per hour. As it moves, it pulls all the planets along with it. So while Earth is orbiting the sun at 30 kilometers per second, it's also simultaneously traveling with the sun at 230 kilometers per second through the galaxy. These motions combine. Earth is not orbiting the sun in a flat circle that somehow stays in the same place. It's orbiting the sun while the sun moves forward, creating a helical, corkscrew-like path. Imagine a toy train on a circular track. Now imagine that track is sitting on a flatbed truck driving down a road. From above, looking down at the truck, you'd see the train going in circles. But from the side of the road, watching the truck pass by, you'd see the train's motion as a series of loops, moving forward with the truck while also going in circles on the track. That's what Earth's true path through space looks like. A looping, spiraling trajectory, following the sun's motion through the galaxy. This changes how we think about planetary positions. When Earth is on one side of the sun, moving in the same direction the sun is moving through the galaxy, its speed through space is the sun's motion plus Earth's orbital speed, about 260 kilometers per second. 6 months later, when Earth is on the opposite side of the sun, it's moving in the opposite direction relative to the sun's path, so its speed is the sun's motion minus Earth's orbital speed, about 200 kilometers per second. Earth's velocity through the galaxy oscillates over the course of a year. The same is true for all the planets. Mercury, being closest to the Sun and orbiting fastest, has the tightest helix. Its path through space looks like a tightly wound spring. Neptune, orbiting slowly at the outer edge of the solar system, has a more gently spiraling path like a very stretched out coil. All of them are spiraling through space together, bound to the Sun by gravity, moving as a coherent system through the vast emptiness between stars. There's something almost hypnotic about visualizing this, isn't there? Close your eyes for a moment. Well, perhaps keep them open to read, but imagine it clearly. The whole solar system, this enormous structure spanning billions of kilometers, is gliding through space like a ship through an ocean. We're all on this ship together. The Sun is the hull. The planets are passengers. And we're all traveling in the same direction, at the same speed, through the galaxy. Now here's where it gets even more interesting. The solar system doesn't move through the galaxy at random. It has a specific trajectory, a particular orbit around the galactic center. Our Sun, along with hundreds of billions of other stars, is orbiting the supermassive black hole at the heart of the Milky Way galaxy. Just as Earth orbits the Sun orbits the galactic core. But this orbit takes much, much longer. The solar system's orbital period around the galaxy, called a galactic year or cosmic year, is approximately 225 to 250 million Earth years. Think about that for a moment. Let it settle slowly into your mind. In the entire history of human civilization, we have traveled only a tiny, infinitesimal fraction of one complete orbit around the galaxy. When dinosaurs ruled the Earth, the solar system was in a completely different part of the galaxy. The last time we were at this same position in our galactic orbit, the most complex life on Earth was probably some form of reptile or amphibian. Since the solar system formed about 4.6 billion years ago, we've completed roughly 18 to 20 orbits of the galaxy. That's it. Just 18 to 20 trips around the galactic center in the entire lifetime of our planet. The Sun is middle-aged, about halfway through its life expectancy, which means it will probably complete another 20 or so galactic orbits before it eventually expands into a red giant and swallows the inner planets. Time on galactic scales moves slowly. Very, very slowly. The solar system's path around the galaxy isn't a perfect circle either. It's an ellipse, and not only that, but the solar system also bobs up and down relative to the galactic plane as it orbits. The Milky Way is a disc-shaped galaxy, relatively flat, with a bulge at the center. Most of the stars orbit in this flat disk, but orbits aren't perfectly planar. The solar system oscillates above and below the galactic plane as it goes around, completing one full up and down cycle about every 60 to 70 million years. Some scientists have speculated that this oscillation might influence Earth in subtle ways. Every time the solar system passes through the denser part of the galactic disk, we're exposed to more cosmic rays, possibly more comets from the Oort cloud being perturbed, maybe even a slightly higher chance of encountering interstellar dust clouds. There have been suggestions, though they remain controversial, that these passages might correlate with mass extinction events on Earth. The data isn't strong enough to say for sure, but it's an intriguing possibility that our position in the galaxy might affect life on Earth in ways we're only beginning to consider. What we do know for certain is that the solar system moves through different stellar neighborhoods over time. The stars you see in the night sky are our current neighbors, but they won't always be. Over millions of years, we drift past some stars and approach others. The constellations slowly change shape. Polaris, our current North Star, hasn't always been the pole star and won't be in the future. The stars are all in motion relative to one another, each following their own orbits around the galaxy, passing each other like ships in the night. There's a term astronomers use, peculiar velocity. It sounds odd, doesn't it? But it simply means the velocity of an object relative to some larger reference frame. The Sun has a peculiar velocity relative to the average motion of nearby stars. We're not moving exactly the same way our neighbors are moving. We're each on slightly different paths, slightly different speeds, orbiting the galaxy in our own particular trajectories. The Sun happens to be moving toward a point in the sky near the constellation Hercules at about 20 kilometers per second, relative to the local standard of rest, the average motion of nearby stars. This means that if you could somehow float motionless relative to the average local stars, you'd see the Sun and Earth and all of us zooming past you at 20 kilometers per second. We're all wanderers, drifting through the galaxy, never staying in one place, never truly at rest. Even the concept of place becomes a bit slippery when you think about it on cosmic scales. Where is Earth really? Here, certainly. But here is somewhere different than it was a moment ago, and somewhere different than it will be a moment from now. Let's pause and breathe for a moment. We've covered a lot of ground, or rather, a lot of space. You're spinning at over 1,000 kilometers per hour due to Earth's rotation. You're orbiting the Sun at 107,000 kilometers per hour. The Sun is moving through the galaxy at 828,000 kilometers per hour, carrying you with it, and the entire solar system is slowly circling the galactic center over the course of 225 million years. Motion within motion, journeys within journeys, like Russian dolls of cosmic movement. And believe it or not, we're not done yet. The galaxy itself is moving. But before we get there, we need to talk about something subtle and beautiful and often misunderstood. The barycenter of the solar system, the point around which everything actually orbits. That's our next gentle destination. There's a common misconception about how orbital systems work. People picture planets orbiting around the Sun as if the Sun is a fixed point in space, stationary and unmoving, while the planets circle around it. But this isn't quite right. Nothing in the universe is truly stationary. Even the Sun moves, responding to the gravitational pulls of the planets. And the place where this becomes most interesting, most elegant really, is a point called the barycenter. The barycenter is the center of mass of a system. It's the balance point, the spot around which all the objects in the system orbit. For a simple system like Earth and Moon, the barycenter is the point where you could balance them if you had a very, very long lever. For the solar system, it's the point where the combined mass of the Sun and all the planets balances out. Here's the thing that surprises people. The barycenter of the solar system is not at the center of the Sun. It's not even always inside the Sun. Depending on the positions of the planets, especially Jupiter, which is by far the most massive planet, the solar system's barycenter can actually be just outside the Sun's surface. The Sun wobbles around this point as the planets orbit, executing a complex dance that responds to the ever-changing configuration of planetary positions. Imagine two dancers holding hands and spinning. If they're the same size and mass, they'll rotate around a point right between them. But if one dancer is much larger and heavier, the rotation point shifts toward the larger dancer. They're still both spinning, but the smaller dancer makes a big circle while the larger one makes a small circle. That's what's happening with the Sun and planets. The Sun is the big dancer, and the planets, especially Jupiter, are the smaller ones. Both are orbiting the barycenter, but the Sun's orbit around it is quite small compared to the planet's orbits. Jupiter is so massive, about 318 times the mass of Earth, that it significantly influences where the barycenter sits. When Jupiter is aligned with the other giant planets on one side of the Sun, they can shift the barycenter to just outside the Sun's surface. The Sun responds by wobbling, making a small loop around this point. The effect is small, just a few 100,000 kilometers compared to the Sun's radius of about 700,000 kilometers. But it's measurable and real. This wobble is actually how astronomers detect planets around other stars. We can't see most exoplanets directly. They're too small and too dim compared to their stars. But we can see the star wobble slightly as the planet orbits. By measuring this wobble carefully, we can infer the presence of planets we can't directly observe. It's detective work on a cosmic scale, reading the subtle movements of stars to deduce what companions they might have. The barycenter concept reveals something profound about gravity. Gravity isn't a one-way force. It's not just the Sun pulling on Earth. Earth pulls on the Sun too, just with much less effect, because of the enormous difference in mass. Newton's third law applies even here. For every action, there's an equal and opposite reaction. The Sun pulls Earth into orbit, and Earth pulls the Sun into a tiny wobble. It's mutual, it's reciprocal. The universe is full of these quiet partnerships. For the Earth-Moon system, the barycenter is particularly interesting. The Moon is large relative to Earth, about 181 of Earth's mass, so their common center of mass is actually about 4,700 kilometers from Earth's center. That's inside Earth, yes, but not at Earth's center. So both Earth and Moon orbit this point. Earth makes a small circle, while the Moon makes a much larger one. If you could watch from space, you'd see Earth itself wobbling slightly as the Moon orbits. We don't notice this wobble in everyday life, but it's there. A gentle cosmic sway that's been going on for billions of years. This wobbling has consequences. It affects the tides, of course. The Moon's gravity creates the bulge of water we call tides, but it also affects Earth's rotation over very long timescales. The gravitational interaction between Earth and Moon is gradually slowing Earth's spin and pushing the Moon farther away, as we mentioned earlier. It's a transfer of angular momentum, mediated through the barycenter, playing out over geological ages. Now, expand this thinking to the whole solar system. Every planet pulls on the Sun. Every moon pulls on its planet. Every asteroid contributes its tiny tug. The barycenter of the solar system is constantly shifting as planets move through their orbits. When all the giant planets align on one side of the Sun, a rare occurrence, the barycenter shifts significantly outward. When they're spread out on different sides, the barycenter is closer to the Sun's center. The Sun wobbles in response, tracing out a complex, chaotic-looking path through space over time. Scientists have calculated and plotted the Sun's motion relative to the solar system barycenter over decades and centuries. It looks a bit like a scribble, a tangled knot of loops and curves. This is the real motion of the Sun, not a simple glide through space, but a complicated dance responding to the gravitational choreography of its planetary family. And we, on Earth, are part of that dance, contributing our small gravitational pull to the overall pattern. There's something almost philosophical about the barycenter. It's a point in space where nothing actually exists. It's not a physical object. You couldn't visit it or touch it. It's purely mathematical, a concept, a balance point. And yet everything in the solar system organizes itself around this empty point. Mass and motion and gravity all conspire to create this invisible anchor, and then everything orbits it. The universe, it seems, doesn't need tangible centers. Abstract mathematical points work just fine. This is true on larger scales too. The Milky Way galaxy has a barycenter, though we usually just call it the galactic center. That's where the supermassive black hole sits, Sagittarius AE, a monster with about 4 million times the mass of the Sun. The black hole doesn't create the barycenter exactly. Rather, the combined mass of the entire galaxy determines where the center of mass is, and the black hole just happens to sit very close to it. Everything in the galaxy, including our solar system, orbits this point. Even galaxy clusters have barycenters. Groups of galaxies orbit around their common center of mass, pulled together by gravity, swirling in immense cosmic ballet that plays out over billions of years. It's barycenters all the way up, each system nesting inside a larger system, each with its own balance point, its own invisible anchor. Let's return to Earth for a moment, to something more personal. You are orbiting the barycenter of the solar system right now. Not just orbiting the Sun, but orbiting this shifting, moving point that dances around near the Sun's center. Your path through space is determined by this point, responding to the invisible influence of every massive object in the solar system. Jupiter's position affects where you are. Saturn's orbit influences your trajectory. You're connected to the entire solar system through gravity, part of a vast, interconnected web of motion and mass. The ancient idea of the cosmos as a great chain of being, where everything is connected to everything else, turns out to be true in a physical sense. Not through divine intervention or mystical forces, but through gravity, that weakest and yet most far-reaching of all forces. Every atom in your body pulls on every other atom in the universe, and every other atom pulls back. The forces are infinitesimally small for distant objects, but they're real. You are, quite literally, connected to everything. Here's a gentle thought experiment as we prepare to move to the next section. Imagine you could somehow mark the path Earth takes through space with a glowing trail. After one orbit around the Sun, 1 year, you'd see a helix, a spiral path. But this spiral itself is moving because the Sun is moving. So after many years, you'd see the helix stretched out across the galaxy, a long spiraling thread tracing Earth's journey. And if you could mark the barycenter's position over time, you'd see that Earth's helix wobbles slightly around another path, the Sun's own complex motion around the barycenter, paths within paths, spirals within spirals, motion within motion. It's beautiful when you think about it. Dizzyingly complex perhaps, but beautiful. The universe doesn't do anything simply when it can do it elegantly and intricately instead. And through it all, through all these nested motions and invisible balance points, you remain here, breathing softly, feeling still, experiencing the profound peace of a quiet moment while racing through space in ways you cannot feel. Let that paradox settle in your mind. Let it be okay not to feel the motion. The stillness is real, the motion is real, both are true at the same time, and there's no contradiction. That's the universe we live in, layered, subtle, full of things happening beneath the surface of perception. Now gently, let's zoom out even further. We've talked about Earth's motion, the solar system's motion, the barycenter. Next, we need to talk about the galaxy itself, the Milky Way, our cosmic home, and the way it moves through the universe. Take a breath. Relax your shoulders. Let's drift into the galactic scale. The Milky Way galaxy is home. Not just Earth, not just the solar system, but the entire galaxy is our home in the deepest sense. It contains everything we've ever seen with our own eyes. Every star, every nebula, every object visible in the night sky, except for a few fuzzy patches that turn out to be other galaxies. About 200 to 400 billion stars, uncountable planets, vast clouds of gas and dust, all bound together by gravity into a great spiral structure spanning about 100,000 light-years across. And this entire structure is moving. Galaxies don't sit still in space. They move relative to each other, pulled by gravity, pushed by the expansion of space itself, participating in a cosmic flow that's playing out across the entire universe. The Milky Way is moving in several different ways simultaneously, just as Earth is. And understanding these motions requires us to step back and look at the bigger picture. Our local group of galaxies, our supercluster, and ultimately the structure of the observable universe itself. Let's start locally. The Milky Way is not alone. It's part of a small cluster of galaxies called the local group, which contains about 80 known galaxies, though most of them are small dwarf galaxies. The two largest members are the Milky Way and the Andromeda galaxy, each with their retinue of smaller satellite galaxies orbiting them. The third largest is the Triangulum galaxy. Together, these galaxies are all orbiting around their common center of mass. Another barycenter, but on a galactic scale. The local group spans about 10 million light-years across. That's enormous compared to the size of individual galaxies, but it's quite small compared to the larger structures in the universe. The galaxies in the local group are gravitationally bound to each other, meaning they're not being separated by the expansion of space. Instead, they're orbiting around each other in a slow, stately dance that will play out over billions of years. And here's something remarkable. The Milky Way and Andromeda are moving toward each other. They're on a collision course. Right now, Andromeda is approaching us at about 110 kilometers per second. In about 4.5 billion years, give or take, the two galaxies will collide. But don't worry, it's not the kind of collision where things smash into each other. Galaxies are mostly empty space. When they merge, it's more like two swarms of bees passing through each other, with stars zipping past, other stars, but almost never actually colliding. The two galaxies will pass through each other, then swing back together, then pass through again, gradually merging into a single larger elliptical galaxy that astronomers have playfully nicknamed Milkomeda. This merger is our galaxy's ultimate fate, at least on the timescale of billions of years. The Milky Way won't exist forever as a distinct spiral galaxy. It will become something new, something different, a cosmic metamorphosis that won't complete until long after our sun has died. Earth, if it still exists, will find itself in a very different-looking night sky, surrounded by the stars of two merged galaxies, orbiting an older, cooler sun, or perhaps having been flung off into intergalactic space by the gravitational chaos of the merger. But this collision is billions of years away. For now, let's talk about how the Milky Way moves through space in the present era. The galaxy has several types of motion, each on a different scale. First, the galaxy rotates. Just as the solar system has planets orbiting the sun, the galaxy has stars orbiting the galactic center. But galaxies don't rotate like solid objects. Different parts rotate at different speeds. The stars near the center orbit quickly, completing a circuit in a few million years. Stars in the outer regions, like our sun, orbit much more slowly, taking 225 to 250 million years to complete one revolution. This differential rotation means the spiral arms you see in pictures of the galaxy aren't fixed structures. They're density waves, regions where stars temporarily bunch up as they orbit, creating the appearance of arms, even though individual stars move in and out of the arms over time. The sun's orbital speed around the galactic center is about 230 kilometers per second, as we mentioned before. But this is just the speed of the sun relative to the galactic center. The galaxy itself is also moving relative to other galaxies, relative to the local group, relative to the cosmic microwave background radiation that fills the universe. Each frame of reference gives a different velocity, and all of them are valid. Relative to the local group's center of mass, the Milky Way is moving at about 100 kilometers per second. The entire local group is moving relative to nearby galaxy groups and clusters. And all of these nearby structures are being pulled toward a massive concentration of matter called the Virgo supercluster, which is being pulled toward an even larger structure called the Great Attractor, which is being pulled toward the Shapley supercluster. It's motion nested within motion, on scales that beggar the imagination. There's a flow to the universe, a cosmic current. Galaxies don't move randomly. They stream along paths determined by the gravitational pull of massive structures. The Milky Way is part of a flow of galaxies moving toward a region of space that contains the Virgo cluster and other massive galaxy clusters. Astronomers have mapped these flows, creating beautiful visualizations that show galaxies streaming along cosmic filaments, the large-scale structure of the universe, like currents in an ocean. The term Great Attractor sounds dramatic, doesn't it? It's a region of space about 250 million light-years away, in the direction of the constellations Centaurus and Hydra, where an enormous concentration of mass is pulling on everything nearby, including our local group. We can't see it directly because it's hidden behind the dust and gas of the Milky Way's galactic plane, but we can detect its presence by measuring the motion of galaxies. Everything in our part of the universe is streaming toward it at about 600 kilometers per second. But wait, there's more. Beyond the Great Attractor lies an even larger structure, the Shapley supercluster, a concentration of about 10,000 galaxies. The Great Attractor itself is being pulled toward Shapley, and our local group, carried along by these flows, is ultimately heading in that direction too. Though we'll never actually reach it because the expansion of space will eventually win out. The most distant structures are receding from us faster than we're moving toward them, pulled away by the expansion of the universe itself. This brings us to the largest scale motion of all, the motion relative to the cosmic microwave background radiation. The CMB is the afterglow of the Big Bang, radiation that fills the entire universe and provides a sort of ultimate reference frame. When we measure our velocity relative to the CMB, we find that the local group is moving at about 630 kilometers per second toward a point in the sky near the constellation Leo. This is the sum of all the various motions, the Milky Way's motion within the local group's motion through space, all the flows and pulls and drifts that affect us. So what's the total picture? Earth spins. Earth orbits the Sun at 30 km/s. The Sun orbits the galactic center at 230 km/s. The galaxy moves within the local group at 100 km/s. The local group streams through space at 630 km/s relative to the CMB. These velocities don't simply add up because they're in different directions, but the point is clear. Earth is moving very, very fast through space in multiple overlapping ways. You are not still. You have never been still. You will never be still. You are a traveler through the cosmos, whether you ever leave your hometown or not. There's something profound about this. Every person who's ever lived, every civilization, every moment of human history has occurred during this cosmic journey. We're not on a planet that sits in a fixed location. We're on a spaceship, careening through the universe at breakneck speed, orbiting a star that's orbiting a galaxy that's streaming through space toward distant structures we'll never reach. We're explorers, all of us, whether we realize it or not. The scale of these motions is hard to wrap your mind around. Light itself, traveling at 300,000 kilometers per second, would take 100,000 years to cross the Milky Way from edge to edge. The distances between galaxies are measured in millions of light years. The structures that pull on our galaxy are hundreds of millions of light years away. And yet gravity reaches across all these distances, gently pulling, constantly influencing, creating flows and streams and movements that play out over billions of years. Let's pause here and breathe. We've traveled far conceptually, from Earth's surface to the solar system, to the galaxy, to the local group, to the large-scale structure of the universe. Each zoom out reveals another layer of motion, another way we're traveling through space. And through it all, you remain here, in this moment, breathing softly, feeling the weight of your body against whatever you're resting on, experiencing stillness even as you race through space at hundreds of kilometers per second. The galaxy moves, and you move with it. The universe flows, and you flow with it. You are not separate from any of this. You are part of the cosmos, literally made of atoms forged in ancient stars, organized by chance into a conscious being capable of contemplating its own motion through space. That's worth pausing to appreciate, isn't it? Now, let's turn our attention to something more subtle, but equally fascinating. The mechanics of how Earth actually moves through space. The orbital dynamics. The complex interplay of forces and velocities that keep everything stable. This is where physics really shines, where mathematics describes the elegant choreography of cosmic motion. Gently now, let's explore the deeper mechanics. We've talked about the various movements, rotation, orbital motion, galactic drift, but we haven't really examined how these movements work, what keeps them stable, what prevents everything from either flying apart into the void or crashing together in a chaotic jumble. The answer, as you might expect, is gravity. But gravity isn't just a simple attractive force. It creates dynamics, patterns, stability, and beautiful mathematical relationships that have taken humanity centuries to fully understand. Let's begin with the most fundamental concept: orbital velocity. An object in orbit is continuously falling toward the object it's orbiting, but it's also moving sideways fast enough that it keeps missing. Earth is falling toward the Sun, but it's moving sideways at just the right speed, that by the time it's fallen, the distance it would have fallen in a straight line. The sun has moved out of the way. Or more accurately, the curvature of Earth's path matches the curvature of space around the sun. The result is a stable orbit. The faster an object is moving, the higher it can orbit without falling in. The slower it moves, the lower its orbit. There's a precise relationship, discovered by Johannes Kepler in the early 1600s, and later explained by Newton's law of gravitation. For any given orbital distance, there's exactly one speed that produces a stable circular orbit. Move faster, and you'll climb to a higher orbit, or even escape entirely. Move slower, and you'll drop to a lower orbit, or eventually crash into the central body. For Earth, orbiting at about 150 million kilometers from the Sun, the required speed is about 30 kilometers per second. This is the speed at which gravity's inward pull exactly balances the outward pull of inertia, the tendency of a moving object to continue in a straight line. It's a perfect balance, a dynamic equilibrium that's been maintained for billions of years. If Earth were suddenly stopped in its orbit, it would fall straight into the Sun, taking about 64 days to reach the surface. If it were suddenly accelerated to about 42 kilometers per second, it would escape the Sun's gravity entirely and drift off into interstellar space. This balance is what makes orbits stable. Small perturbations, like the gravitational tugs from other planets, cause wobbles and variations, but the basic orbit remains intact. It's self-correcting in a way. If Earth moves a bit faster in its orbit, it climbs slightly higher, where orbital speed is lower, so it naturally slows down. If it slows down, it drops slightly lower, where orbital speed is higher, so it naturally speeds up. The orbit breathes, flexes, adjusts, but maintains its overall character. Kepler discovered 3 laws that describe orbital motion, laws that Newton later showed were direct consequences of his theory of gravitation. The first law states that orbits are ellipses, not circles, with the central body at one focus of the ellipse. Earth's orbit is nearly circular, but it's still an ellipse, which is why our distance from the Sun varies over the course of a year. The second law states that a line from the Sun to Earth sweeps out equal areas in equal times. This is a fancy way of saying that Earth moves faster when it's closer to the Sun and slower when it's farther away. At perihelion, Earth is moving about 30.3 kilometers per second. At aphelion, it's moving about 29.3 kilometers per second. It's a small difference, but it's there, a subtle variation in the cosmic dance. The third law gives a relationship between orbital period and distance. The square of the orbital period is proportional to the cube of the average distance from the Sun. This means that if you know how far a planet is from the Sun, you can calculate how long its year is, and vice versa. It's a beautiful mathematical relationship, elegant in its simplicity. And it works not just for planets orbiting the Sun, but for any object orbiting any other object under the influence of gravity. Newton's great insight was that these laws weren't arbitrary. They emerged naturally from his law of universal gravitation and his laws of motion. Gravity weakens with the square of distance, double the distance, and gravity is 1/4 as strong. This inverse square relationship produces exactly the orbital behavior, Kepler observed. It was one of the great unifications in the history of science, showing that the same force that makes an apple fall from a tree also keeps planets in their orbits. But Newton's laws are only approximations, extremely good approximations, but approximations nonetheless. Einstein showed that gravity isn't actually a force in the traditional sense. It's a curvature of space-time. Massive objects like the Sun bend the fabric of space-time around them, and other objects moving through that curved space follow paths that look like orbits to us. Earth isn't being pulled toward the Sun by a force, exactly. It's following the straightest possible path through curved space-time, and that path happens to be an ellipse around the Sun. For most purposes, Newton's description is perfectly adequate. The corrections from Einstein's general relativity are tiny for planets orbiting the Sun. They only become noticeable for very precise measurements or for objects in very strong gravitational fields. Mercury, being closest to the Sun, shows the largest relativistic effects. Its orbit precesses, slowly rotating, slightly more than Newton's laws predict. This precession was actually one of the first confirmations of general relativity. Now, let's think about the stability of the solar system as a whole. You might imagine that with 8 planets, all tugging on each other gravitationally, the system would eventually become chaotic, with planets crashing into each other or being flung out into space. And you'd be right, in a sense. Over extremely long timescales, billions and billions of years, the solar system is chaotic. Small changes in initial conditions can lead to large changes in outcomes. Computer simulations suggest that there's a small but non-zero chance that Mercury could be ejected from the solar system or even collide with Venus in the next few billion years. But on shorter timescales, mere millions of years, the system is remarkably stable. The planets have settled into a configuration where they don't strongly perturb each other. They're in what's called a resonance pattern, where their orbital periods are related by simple ratios that prevent close encounters. Jupiter and Saturn, for instance, have an orbital resonance where Saturn completes 2 orbits for every 5 that Jupiter completes. This keeps them from ever getting too close to each other. These resonances are everywhere in the solar system. Many of Jupiter's moons are in resonances with each other. The asteroid belt has gaps, called Kirkwood gaps, at distances from the Sun, where an asteroid would be in resonance with Jupiter and would get perturbed out of that orbit. Saturn's rings have gaps carved by resonances with its moons. Resonances create order out of what could otherwise be chaos, stabilizing the system and creating patterns. There's something almost musical about orbital resonances. The periods of planets are like notes in a chord, related by simple mathematical ratios, harmonizing in a way that prevents dissonance. The ancients spoke of the music of the spheres, believing that planetary motions created inaudible harmonies. They were wrong about the mechanism. There's no actual sound in space, but they were right in spirit. There is harmony in the solar system, mathematical harmony, expressed through the language of orbital mechanics. Now consider the energy involved in all this motion. Earth, with a mass of about 6x 10^24 kilograms, moving at 30 kilometers per second, has an enormous amount of kinetic energy. If you could somehow capture that energy, it would be enough to power human civilization for millions of years. But that energy is locked up in orbital motion, inaccessible to us, constantly balanced against the potential energy of Earth's position in the Sun's gravitational field. The total energy of Earth's orbit, kinetic plus potential, is negative, which is what keeps Earth bound to the Sun. If the total energy were positive, Earth would have enough energy to escape. The boundary between bound and unbound orbits is called the escape velocity. For Earth's position in the solar system, the escape velocity is about 42 kilometers per second. We're moving at 30 kilometers, comfortably below escape velocity, comfortably bound to the Sun for the foreseeable future. All of this, the velocities, the energies, the resonances, the stability, emerges from the elegant simplicity of gravity, a force that weakens with the square of distance, combined with the laws of motion, produces the rich complexity of the solar system. It's remarkable, really. From such simple rules, such intricate patterns emerge. The universe seems to delight in taking simple principles and weaving them into complex tapestries. Let's think for a moment about what this means for Earth's journey through space. Our path isn't random, it's precisely determined by physics, by the masses and positions and velocities of all the objects in the solar system. If you know the current state exactly, every position, every velocity, you could in principle calculate Earth's position millions of years in the future, or millions of years in the past. The solar system is deterministic, at least on timescales where chaos doesn't dominate. This is both comforting and slightly unsettling. Comforting because it means we're not going to suddenly veer off course and crash into Mars. The orbits are stable, predictable, reliable, but unsettling because it implies a kind of cosmic mechanism, a clockwork universe where everything is determined by past conditions, where there's no room for randomness or free will, at least not in the motion of planets. But this determinism breaks down at the quantum level and in chaotic systems over long timescales. The universe isn't really a clockwork, it's more like a jazz improvisation, structured enough to have coherence, but with enough freedom and randomness to remain unpredictable and creative. The solar system operates within strict physical laws, but within those laws, there's room for variation, for uncertainty, for surprising outcomes over geological time. As you lie there, breathing slowly, you are part of this system. Every atom in your body responds to gravity. If you could measure precisely enough, you'd detect the gravitational pull of Jupiter, of Saturn, of every planet. These forces are tiny, far too small to feel, but they're real. You are gravitationally connected to the entire solar system, part of the same orbital dynamics that govern Earth's path through space. Let's take a moment to rest here, to let the mechanics settle. Gravity, inertia, velocity, energy, resonance. These aren't just abstract concepts. They're the principles that govern your motion through space, the forces that have shaped your entire existence, the mathematics underlying the cosmic ballet in which you're a participant. Breathe in the elegance of it. Breathe out any confusion. The details might be complex, but the underlying truth is simple. You are held, gently but firmly, in the embrace of gravity, dancing through space in patterns as old as the solar system itself. Next, let's explore something more visceral, more connected to your daily experience, how Earth's motion affects what you see in the sky, how it shapes the seasons, how it determines when and where you can see stars and planets. The motion we've been describing isn't just abstract physics. It has consequences you can observe every single night. Softly now, let's turn our eyes upward. The night sky is a clock, a calendar, and a map all at once. Every motion we've discussed, Earth's rotation, its orbit, the solar system's path through the galaxy, leaves its mark on what you see when you look up. The sky changes from hour to hour, season to season, year to year, millennium to millennium. And if you know what to look for, you can read these changes like a book, detecting motion you can't directly feel through patterns in the stars above. Let's start with the most obvious effect, the daily motion of the sky. As Earth rotates, the stars appear to wheel overhead, rising in the east and setting in the west. The sun, moon, and planets follow this same apparent motion, all of them participating in the grand celestial rotation. But it's not them moving, it's you, spinning beneath a relatively fixed sky. If you watch the stars over the course of a night, you'll notice they move in arcs across the sky. Stars near the celestial equator rise due east, climb to their highest point in the southern sky, if you're in the northern hemisphere, and set due west. Stars near the celestial poles trace smaller circles, and some, the circumpolar stars, never set at all, just circle around the pole throughout the night. The North Star, Polaris, sits very close to the north celestial pole, so it barely moves at all, remaining fixed in the north while all other stars wheel around it. This rotation has been obvious to humans since prehistoric times. Ancient cultures built monuments aligned to celestial events. Stonehenge, the pyramids of Egypt, countless other structures that track the rising and setting points of the sun and stars. These weren't just religious or ceremonial. They were practical tools for keeping time and predicting seasons, essential for agricultural societies that needed to know when to plant and harvest. But the rotation is only the beginning. Earth's orbit around the sun creates another layer of celestial motion. As Earth moves along its orbit, our nighttime perspective changes. In December, Earth is on one side of the sun, and the constellations visible at night are those in the direction opposite the sun. In June, Earth is on the other side, and we see a completely different set of constellations at night. The sun appears to move through the zodiac constellations over the course of a year, not because the sun is actually moving relative to those stars, but because Earth's changing position changes our line of sight. This annual motion of the sun through the zodiac is called the ecliptic. It's the projection of Earth's orbital plane onto the celestial sphere. The moon and planets also stay close to the ecliptic because they orbit roughly in the same plane as Earth. If you want to know where to look for planets in the night sky, look along the ecliptic. They'll be somewhere in one of the zodiac constellations. The planets don't stay fixed relative to the stars, though. They wander. That's why the ancient Greeks called them planets, meaning wanderers. As Earth and another planet both orbit the sun, the relative positions change. Sometimes a planet appears to move eastward through the stars, the normal prograde direction. Sometimes it appears to stop, then move westward in retrograde motion, then stop again and resume eastward motion. This retrograde motion puzzled ancient astronomers for centuries. It seemed chaotic, unpredictable. The answer, as Copernicus realized, is that it's an effect of Earth's motion. When Earth, moving faster in its inner orbit, overtakes an outer planet like Mars, the planet appears to move backward relative to the stars, just as a car you're passing on the highway appears to move backward relative to distant mountains. There's no actual backward motion. It's entirely due to changing perspective as both planets orbit the sun. Once you understand this, the apparent chaos resolves into elegant, predictable patterns. Earth's axial tilt creates another profound effect: the seasons. The tilt means that different parts of Earth receive different amounts of sunlight at different times of year. When the northern hemisphere is tilted toward the sun, it's summer there. Days are long, the sun is high in the sky, and more energy reaches the surface. 6 months later, when the northern hemisphere is tilted away, it's winter. Days are short, the sun is low, less energy arrives. The southern hemisphere experiences the opposite pattern, with summer when the north has winter and vice versa. This tilt also affects which stars are visible. In summer, when night is short, you can only see stars in a limited band across the sky. In winter, with longer nights, you can see a much wider swath of the celestial sphere. Some constellations are considered winter constellations or summer constellations, not because they're only visible in those seasons, but because that's when they're highest in the sky, at a convenient viewing time. Orion, for instance, is a winter constellation in the northern hemisphere, dominant in the evening sky from December through February. The tilt of Earth's axis isn't fixed in space, though. It precesses, slowly wobbling like a spinning top, completing one full cycle every 26,000 years. This is called axial precession, or the precession of the equinoxes. Right now, Earth's north pole points roughly toward Polaris, making it our North Star. But 5,000 years ago, the pole pointed toward a different star, Thuban, in the constellation Draco. In another 12,000 years, it will point toward Vega. The celestial poles move in slow circles through the sky, and over millennia. This changes which stars are circumpolar, which stars are visible from different latitudes, even which constellations the sun appears in at the equinoxes and solstices. This precession is caused by the gravitational tugs of the sun and moon on Earth's equatorial bulge. Remember, Earth is slightly flattened at the poles and bulges at the equator. This bulge feels a slight torque from external gravitational forces, causing the axis to precess. It's a subtle effect, but over thousands of years, it's noticeable. Ancient astronomers, comparing their observations to records from centuries earlier, could detect the slow drift of the equinox points through the zodiac. This is why the Age of Aquarius is a real astronomical phenomenon, not just a song lyric. We're slowly transitioning from the sun's equinox position in Pisces to Aquarius, a transition that takes about 2,000 years. Now let's think about the solar system's motion through the galaxy. Does this affect what we see in the sky? On human timescales, barely. The stars are so distant that even though we're moving at 230 kilometers per second through the galaxy, the constellations change shape very, very slowly. Over tens of thousands of years, yes, the stars' relative positions shift noticeably. Over millions of years, the constellations become unrecognizable. But in a human lifetime, the changes are too small to notice without precise instruments. There is one way you can detect the solar system's motion through the galaxy: by measuring the Doppler shift of starlight. Stars in the direction we're moving appear slightly blue-shifted. Their light is compressed, shifted toward shorter wavelengths. Stars in the opposite direction appear slightly red-shifted. This is the same Doppler effect that makes an ambulance siren sound, higher pitched when approaching and lower when receding. With sensitive instruments, astronomers can measure these shifts and map out the motion of stars relative to us, creating a three-dimensional map of how our stellar neighborhood is moving through the galaxy. The European Space Agency's Gaia mission has been doing exactly this, measuring the positions and motions of over 1 billion stars with extraordinary precision. The data reveals the complex choreography of the Milky Way, streams of stars moving together, remnants of smaller galaxies that merged with ours billions of years ago, clusters orbiting the galactic center at different speeds. It's a cosmic archaeology, reading the history of our galaxy in the motions of stars. Here's something wonderful to ponder. The light you see from distant stars left those stars years, decades, or centuries ago. When you look at Sirius, the brightest star in the night sky, you're seeing light that left it about 8.6 years ago. When you look at Betelgeuse in Orion, you're seeing light from about 550 years ago, from the time of the Renaissance. And those stars were in slightly different positions when they emitted that light than they are now. You're looking at the past, seeing stars as they were, not as they are, observing a universe in motion, but seeing it time-delayed. The sky, then, is not a snapshot, but a historical record. Every photon that enters your eye is a messenger from the past, carrying information about where something was and what it was doing at some earlier time. The universe doesn't have a single now that extends across all of space. Light travels at a finite speed, so what you see is always what was, not what is. This is one of the strange implications of relativity. Simultaneity is relative, and the present moment is different for observers in different locations or states of motion. Let's bring this back to something more immediate. How can you use your own observations to detect Earth's motion? Here are a few ways, some obvious, some subtle. First, watch a sunset. The sun sinks below the western horizon because Earth is rotating, carrying you eastward and rotating the sun out of view. If you could stop Earth's rotation for just a moment, the sun would freeze in place in the sky. The sunset is direct evidence of Earth's spin, evidence you can see with your own eyes every single evening. Second, watch the moon over several nights. Notice how it changes position relative to the stars, drifting eastward about 13 degrees per day. This is the moon's orbital motion around Earth, visible and obvious if you pay attention. The phases of the moon, new, crescent, quarter, gibbous, full, are caused by the changing angle between the sun, moon, and Earth as the moon orbits. When the moon is between Earth and sun, we see the new moon. When Earth is between moon and sun, we see the full moon. The phases are a calendar of the moon's orbital position. Third, note which constellations are visible at different times of year. In January, look south after sunset and you'll see Orion. In July, try to find Orion. You can't because it's in the daytime sky, on the same side of Earth as the sun. This seasonal change in the night sky is direct evidence of Earth's orbit around the sun. Ancient astronomers used these changes to mark the passage of the year long before calendars were invented. Fourth, if you're patient and have a good star chart, you can observe stellar parallax yourself. Choose a relatively nearby star and measure its position relative to more distant background stars. Wait 6 months until Earth is on the opposite side of its orbit and measure again. the nearby star will have shifted slightly. It's a tiny shift, even for the nearest stars, less than 1 arcsecond, which is 1/3600th of a degree. But with careful measurements, it's detectable. You'll be replicating the observations that proved Earth orbits the Sun and measuring the vast distances between stars using nothing but patience and geometry. The sky is full of evidence of motion if you know where to look. The daily wheeling of stars speaks of rotation. The annual march of constellations speaks of Earth's orbit. The wandering of planets speaks of the complex orbital ballet of the solar system. The slow drift of the equinox points speaks of axial precession. Everything moves, and everything leaves traces. There's something deeply satisfying about connecting the abstract physics we've been discussing to concrete observations you can make yourself. You don't need fancy equipment. You don't need advanced degrees. You just need patience, attention, and a willingness to watch the sky over time. The universe reveals its secrets slowly, gently, to anyone who takes the time to look. As we prepare to move to our next section, take a moment to visualize this. Imagine you're lying outside on a clear night, far from city lights, looking up at the stars. The Milky Way stretches overhead, a river of light. The stars are fixed, or seem to be, holding their patterns. But you know now that this fixity is an illusion. Everything is moving. The stars are orbiting the galaxy at different speeds. You're moving, carried by Earth's rotation and orbit. The galaxy itself is streaming through space. And yet the sky appears still, peaceful, eternal. Motion and stillness, both true at once. Let's drift now towards something more philosophical, more contemplative. We've covered the mechanics of Earth's motion, the scales involved, the evidence in the sky. But what does it all mean? How should we think about our place in this vast, moving cosmos? Gently, let's explore the deeper implications. What does it mean to be moving through space at hundreds of kilometers per second and not feel it? What does it mean to be on a planet that's been journeying through the galaxy for billions of years, that will continue long after you're gone? These aren't just scientific questions. They're philosophical ones, touching on how we understand our place in the universe and what it means to be human in a cosmos that's vastly larger and more dynamic than everyday experience suggests. Let's start with a paradox. You are simultaneously at the center of your own reference frame and utterly peripheral in the larger cosmos. From your perspective, right now, lying there or sitting there, you are still. You are the fixed point around which the rest of the universe moves. The ground is beneath you, the walls are around you. Everything else, Earth, the solar system, the galaxy, moves relative to you. This isn't wrong. This is your valid frame of reference. Physics doesn't privilege any particular viewpoint. Relative to yourself, you're always at rest. But zoom out, adopt a different frame of reference, and you become a tiny mote of dust on a speck of rock orbiting an ordinary star in an unremarkable part of a galaxy that's one among hundreds of billions. From this perspective, you're moving at tremendous speeds, racing through space, participating in cosmic currents that dwarf any human concern. You're peripheral, insignificant, a brief flicker in the long history of the universe. Both perspectives are true. You are simultaneously central and peripheral, still and moving, important and insignificant. This is the profound gift of modern cosmology. It doesn't erase human meaning, but it complexifies it, adds layers, demands that we hold multiple truths at once without collapsing them into a single simple story. The ancient Greeks placed Earth at the center of everything. It was a cosmology that matched human experience and human intuition. We feel still, so we must be still. Everything else moves, so everything else must be orbiting us. It was egocentric in the literal sense, the self at the center. The Copernican revolution displaced us from this central position. Earth orbits the sun, not the reverse. We're not special. We're just another planet. This was experienced by many as a demotion, a loss of significance. If we're not at the center, What does that say about human importance? But there's another way to see it. We're not at the center of the universe, but we're part of the universe. We're not separate observers looking at the cosmos from outside. We're participants, embedded in the very phenomena we're studying. The atoms in your body were forged in stars. You're made of the same stuff as planets and nebulae. You are the universe looking at itself, a way for the cosmos to know itself. Carl Sagan had a beautiful phrase. We are a way for the cosmos to know itself. This captures something essential. Yes, we're tiny and peripheral, but we're also the only things in the entire vast universe, as far as we know, that can understand what a universe is, that can measure cosmic motions, that can feel awe at the scale and beauty of it all. That's not nothing. That's actually pretty remarkable. The motion we've been exploring, Earth's spin, orbit, galactic journey, connects you to the largest scales of space and time. You're not just a person living in a particular time and place. You're a conscious entity riding through the cosmos on a rocky planet, experiencing the universe from within, participating in motions that have been ongoing for billions of years and will continue for billions more. Your individual life is brief, but it's threaded into something vast and ancient. There's a Zen quality to this realization. The more you understand about cosmic motion, the more you realize how little any of it matters to your immediate experience. You're moving at incomprehensible speeds, and yet here you are, breathing slowly, feeling the weight of your body, experiencing the quiet peace of this moment. The motion doesn't diminish the stillness. The vastness doesn't diminish the intimacy of your own consciousness. Big and small, fast and slow, cosmic and personal, they all coexist without contradiction. Buddhism speaks of emptiness, not as a void, but as the lack of intrinsic, independent existence. Everything depends on everything else. You depend on Earth, which depends on the Sun, which depends on the galaxy, which emerged from the initial conditions of the Big Bang. There's no place where you end and the universe begins. You're continuous with everything. The motion of Earth through space is also your motion. You're not on the journey, you are the journey. This perspective can be comforting. When you feel anxious, small, worried about the future, it helps to remember the scale of things. The Earth has been spinning for 4.5 billion years. The solar system has orbited the galaxy 20 times. You are part of something much larger and older than your individual concerns. This doesn't make your problems unreal or unimportant, but it provides context. You're held within a stable system, moving through space on predictable paths, protected by gravity and atmosphere, cocooned in the warmth of a star that will shine reliably for billions of years to come. At the same time, the motion reminds us that nothing is permanent. The constellations will change, the solar system will eventually merge with Andromeda, stars will die, galaxies will disperse. Everything we see, everything we know, is temporary, transient, moving toward an uncertain future. This could be depressing, but it could also be liberating. If nothing lasts forever, then there's no pressure to make things permanent. You can appreciate beauty in the moment, precisely because it's fleeting. The Japanese have a concept called mono no aware, a sensitivity to the transience of things, a gentle sadness mixed with appreciation that comes from recognizing impermanence. Cherry blossoms are beautiful, partly because they don't last. The night sky is precious, partly because the exact configuration of stars you see tonight will never be repeated. Earth's position in its orbit, your location on Earth's surface, the specific moment in cosmic time, all of these factors combine to create a view that's unique and unrepeatable. Here's a thought that might help you sleep, or might keep you awake with wonder, depending on your temperament. Every moment of your life occurs at a unique location in space. You will never return to the same cosmic address twice. Earth is orbiting the Sun is moving through the galaxy is streaming through space. Even if you stay in the same house, in the same bed, for your entire life, you're constantly traveling to new regions of space, seeing new photons from distant stars, breathing atoms that have never been in your location before. You are an explorer, whether you move or not. This realization can change how you experience the present moment. You're not just here, now. You're here in this location, in space that will never be visited again, now in this moment in cosmic time that will never return. Every instant is unique, not just in terms of your personal experience, but in terms of your absolute position in the four-dimensional fabric of space-time. You're tracing a path through the universe that's yours alone, a path that's never been traced before and will never be traced again. Does this make your life more meaningful? That's up to you. Meaning is something we create, not something we find. The universe doesn't assign meaning to human lives. It doesn't assign meaning to anything. It just unfolds according to physical laws, creating patterns and structures, and, occasionally, conscious beings who can ask questions about meaning. But this lack of inherent meaning is actually a kind of freedom. You get to decide what matters. You get to choose how to respond to the vast, ancient, moving cosmos you find yourself embedded in. Some people find comfort in feeling connected to something larger than themselves. The motion of Earth through space is a reminder of that connection. You're not isolated. You're part of Earth's biosphere, which is part of the solar system, which is part of the galaxy, which is part of the universe. Everything's connected, all the way up and all the way down. Other people find comfort in the opposite, in the realization that despite all this cosmic motion, their immediate experience remains valid and central. The universe can be as vast as it wants, but you're still here, in your body, experiencing this moment, and that's what matters most. Both perspectives are valid. Both can coexist. Let's take a breath here. We've wandered into abstract territory, philosophy and meaning and existence. It's easy to get lost in these questions, to spiral into either cosmic despair or cosmic euphoria. But remember, you don't have to figure it all out tonight. You don't have to reconcile all the contradictions or answer all the big questions. You can just let it all be, the motion and the stillness, the vastness and the intimacy, the temporary and the eternal. The universe is content to be paradoxical. Perhaps you can be too. As we move toward our final sections, let's turn to some specific details we haven't covered yet. The speeds and scales we've mentioned but not fully explored. The numbers that help us grasp just how fast and far we're really traveling. And then, gently, we'll begin to wind down, to bring our journey full circle, to return to where we started with new understanding. Softly now, let's look at the numbers. Numbers can be dry, they can be boring, or they can be astonishing, mind-expanding, almost poetic in their ability to convey scale. Let's try to make the numbers we've been mentioning more concrete, more visceral, more real. Let's see if we can feel, even if only intellectually, just how fast Earth is really moving through space. Start with rotation. At the equator, Earth's surface is moving at about 1,670 kilometers per hour. That's roughly 465 meters per second, or about 1,040 miles per hour. To put that in perspective, the speed of sound at sea level is about 1,135 kilometers per hour. At the equator, you're moving at about 75% of the speed of sound just by standing still. You're almost supersonic from rotation alone. If you're at 45 degrees latitude, roughly the latitude of Minneapolis, Bordeaux or Milan, your rotational speed is about 1,180 kilometers per hour. At 60 degrees, Anchorage, Oslo, St. Petersburg, it's about 835 kilometers per hour. At the poles, your rotational speed is essentially zero. You're just pirouetting in place once every 24 hours. Now add orbital motion. Earth orbits the Sun at an average speed of 29.78 kilometers per second. Let's convert that to more familiar units. That's about 107,200 kilometers per hour, or roughly 66,600 miles per hour. In the time it takes you to read this sentence, say 5 seconds, Earth has traveled nearly 150 kilometers along its orbit. That's the distance from London to Sheffield, or from Los Angeles to San Diego, covered in the time it takes to read a single sentence. Every day, Earth travels about 2.5 million kilometers along its orbit. That's roughly 6.5 times the distance from Earth to the Moon. In a year, Earth travels the entire circumference of its orbit, about 940 million kilometers. That's the distance light travels in about 52 minutes. These speeds are fast, but they're still well below the speed of light, which is about 300,000 kilometers per second, or 1.08 billion kilometers per hour. Earth's orbital speed is about 0.01% of the speed of light, fast by human standards, but a leisurely pace by cosmic standards. Now consider the sun's motion through the galaxy. We've said it's moving at about 230 kilometers per second, which is roughly 828,000 kilometers per hour. This is about 7.7 times faster than Earth's orbital speed around the sun. In 1 second, the sun, carrying Earth with it, moves 230 kilometers. That's the distance from Boston to New York, covered in a single tick of a clock. In 1 day, the sun moves about 19.9 million kilometers through the galaxy. That's more than 50 times the distance from Earth to the Moon. In a year, the sun travels about 7.25 billion kilometers, or about 48.4 astronomical units. That's farther than the distance from the sun to Pluto at its average orbit. The sun takes about 225 to 250 million years to complete one orbit of the galaxy. Let's call it 230 million years for simplicity. In that time, it travels the full circumference of its galactic orbit, about 1.7 trillion kilometers. That's about 180,000 times the distance from Earth to the Sun, or about 180,000 astronomical units. Light, traveling at 300,000 kilometers per second, would take about 180 years to cover that distance. These numbers are almost impossible to truly grasp. The human brain didn't evolve to comprehend distances measured in trillions of kilometers or speeds measured in hundreds of kilometers per second. We're built to understand the scale of things we can see and touch: trees, animals, rivers, mountains. Cosmic scales overwhelm our intuitions. But let's try anyway. Imagine you're traveling in a car at 100 kilometers per hour on a highway. At that speed, you'd need about 16.7 hours to cover the distance Earth travels in 1 second due to rotation at the equator. You'd need about 4.5 days of continuous driving to cover the distance Earth travels in 1 second along its orbit. And you'd need about 96 days of continuous driving to cover the distance the sun moves through the galaxy in 1 second. These scales are just large. Very, very large. Here's another way to think about it. If you could somehow survive standing on the surface of the sun as it moves through the galaxy, you'd experience wind, cosmic wind perhaps, though there's no actual air, at 230 kilometers per second. If that were actual air, it would be the most violent hurricane imaginable, millions of times stronger than any storm on Earth. Of course, there's no air in space, so you'd feel nothing. But the speed is real. The speeds we've discussed so far are relative to the sun or the galactic center. But remember, the galaxy itself is moving. The local group is moving at about 100 kilometers per second relative to its center of mass. And the local group as a whole is moving at about 630 kilometers per second relative to the cosmic microwave background. These velocities don't simply add up because they're in different directions, but the point is that our total motion through the universe is even faster than the numbers we've been citing. If you were to add up all the velocity components, rotation, orbit, solar motion, galactic motion, local group motion, in some kind of absolute sense, you'd find that you're moving at something like 600 to 700 kilometers per second through the universe. That's about 2 million kilometers per hour, or roughly 0.2% of the speed of light. In cosmic terms, you're a sluggish creature. But by human standards, you're blazingly fast, moving at speeds that would make any jet pilot jealous. Let's think about time now, which is intimately connected to motion. We measure time by motion. The rotation of Earth gives us the day, the orbit gives us the year. But cosmic motions occur on much longer timescales. The Sun's galactic orbit takes 225 million years, a period sometimes called a galactic year or cosmic year. Dinosaurs appeared about 230 million years ago, roughly 1 galactic year in the past. They went extinct about 66 million years ago, about 0.3 galactic years ago. Humans have existed for perhaps 300,000 years, about 0.0013 galactic years. Written history covers maybe 5,000 years, about 0.00022 galactic years. On the timescale of galactic rotation, human civilization is a brief flash, barely noticeable. All of recorded history has occurred while the Sun has moved about 0.05% of the way around its current galactic orbit. We haven't budged, cosmically speaking. We're essentially in the same spot we've always been, at least on galactic scales. This is humbling, certainly, but it's also oddly comforting. The universe operates on timescales so long that human concerns, even catastrophes, are barely blips. This doesn't mean human suffering doesn't matter. It absolutely does, to us. But it does provide a kind of perspective. The cosmos is patient. It's been unfolding for 13.8 billion years. It will continue for trillions more, long after the Sun dies, long after the last star flickers out. We get to exist during a brief, bright moment when the universe is full of stars and planets, and possibly life. That's something to appreciate. Let's zoom back in, back to human scale. You personally, in your lifetime, will travel enormous distances through space. If you live 80 years, you'll complete 80 orbits around the Sun, traveling about 75 billion kilometers. That's about 500 times the distance from Earth to the Sun. You'll also travel with the Sun about 584 billion kilometers through the galaxy, about 3,900 times the distance from Earth to the Sun. And you'll participate in the local group's motion through the universe, adding even more distance. All of this while, from your perspective, you might never leave your hometown. The distances are real. The motion is real. But your experience is one of stillness, of being in a place, of inhabiting a location. Both are true. You are simultaneously a cosmic voyager traveling hundreds of billions of kilometers and a local creature living in one small spot. The numbers, large as they are, don't capture everything. They don't capture the elegance of orbital mechanics, the beauty of watching stars wheel overhead, the feeling of connection to something larger than yourself. Numbers are tools for understanding, but they're not the whole story. Still, they're worth knowing. They remind us just how dynamic the universe is, how much is happening beneath the surface of our everyday experience. Take a moment. Breathe. Let the numbers wash over you. Don't try to hold on to them all. Just let them give you a sense of scale, a feeling for the speeds and distances involved. You're moving fast, you're traveling far, and yet here you are, perfectly still, breathing softly, existing in this gentle moment. The paradox continues. Now, as we move toward the conclusion of our journey, let's talk about what we still don't know. Science has revealed so much about Earth's motion, but mysteries remain. There are questions still unanswered, puzzles still unsolved, and that's perfect. That's how science should be. Not a body of fixed knowledge, but an ongoing exploration, always discovering new layers of complexity. Gently, let's explore the edges of our understanding. For all that we've learned about Earth's motion through space, there remain profound mysteries. Science has mapped our movements in extraordinary detail, but each answer raises new questions, and some fundamental aspects of cosmic motion remain puzzling, even mysterious. Let's explore a few of these lingering enigmas, the places where our understanding fades into uncertainty. First, there's the question of dark matter. We know the Sun orbits the galactic center at about 230 kilometers per second. We can calculate how fast it should be orbiting based on the visible matter in the galaxy, the stars, gas, and dust we can see. And here's the problem. The Sun is moving too fast. Given the amount of visible matter, the Sun should be moving slower, and the outer parts of the galaxy should be moving slower still. But they're not. The entire galaxy is rotating faster than it should. The answer, astronomers believe, is dark matter, a form of matter that doesn't emit, absorb, or reflect light, that interacts with ordinary matter only through gravity. Dark matter, if it exists, makes up about 85% of the matter in the universe. It surrounds galaxies in vast halos, providing the extra gravitational pull needed to explain the rotation speeds we observe. The Milky Way is embedded in a dark matter halo that extends far beyond the visible disk, pulling on the stars and gas, shaping the galaxy's motion. But we don't know what dark matter is. We've never detected a dark matter particle directly. We infer its existence from its gravitational effects, but its nature remains elusive. Is it a new type of particle not described by the standard model of particle physics? Is it a modification of gravity itself? Some deviation from Einstein's theory that manifests on galactic scales? We don't know. And until we do, our understanding of galactic motion remains incomplete. We can describe how things move, but we can't fully explain why without invoking this mysterious, invisible substance. Then there's dark energy, even more mysterious than dark matter. The universe is expanding, and not only that, but the expansion is accelerating. Distant galaxies are moving away from us faster and faster. This acceleration requires energy, a lot of energy, enough to overpower the gravitational attraction of all the matter in the universe. This energy, dubbed dark energy, makes up about 68% of the total energy content of the universe. What is dark energy? We don't know. It might be a property of space itself, a kind of intrinsic energy density associated with empty space, what physicists call vacuum energy, or the cosmological constant. It might be a new type of field permeating the universe, something like the Higgs field, but with different properties. Or it might be a sign that our theories of gravity break down on cosmological scales, that we need a new understanding of space-time and gravitation to explain what we see. Dark energy affects Earth's motion only indirectly and very weakly on the scale of the solar system or even the galaxy, but it does affect the large-scale structure of the universe, determining how galaxy clusters move relative to each other, how the universe expands. Our understanding of Earth's place in the cosmos is incomplete without understanding dark energy, and we're nowhere close to solving that mystery. There's also the question of whether Earth's orbit is truly stable over very long timescales. We know it's stable for millions of years. The calculations are clear on that. But what about billions of years? Computer simulations of the solar system's long-term evolution show that the system is chaotic, meaning tiny changes in initial conditions can lead to large changes in outcomes. Over timescales of billions of years, there's a small but non-zero probability that planetary orbits could change dramatically. Mercury might get ejected or collide with Venus. Earth's orbit might be perturbed by gravitational interactions with other planets. These are low-probability events, and they're billions of years in the future, long after the Sun will have evolved into a red giant and likely destroyed the inner planets anyway. But they remind us that even the seemingly eternal motions of planets are temporary, subject to chaos and chance over extremely long timescales. Nothing is forever, not even orbits. Another mystery. What determines the plane of the solar system? All the planets orbit roughly in the same flat plane, called the ecliptic. This makes sense. The solar system formed from a rotating disk of gas and dust, and planets condensed from that disk, so they naturally orbit in the plane of the original disk. But why was the original disk tilted at the particular angle it has? Why is the ecliptic tilted about 60 degrees relative to the galactic plane? The answer probably lies in the conditions when the solar system formed, in the turbulent environment of the stellar nursery where our sun was born. Random motions of gas clouds, gravitational interactions with nearby forming stars, perhaps even the explosion of a nearby supernova All of these could have influenced the orientation of the disk that became our solar system. But we can't rewind time and watch it happen. The specific reasons for the solar system's orientation remain speculative. There's also the mystery of Planet 9, a hypothetical planet that might exist in the outer solar system. Astronomers have noticed that certain distant objects beyond Neptune have strange orbits that seem to be influenced by something massive lurking out there. The orbits cluster in a way that's statistically unlikely to be random. Some astronomers believe there's a planet, perhaps 5 to 10 times the mass of Earth, orbiting the Sun at a distance of 400 to 800 astronomical units, taking 10,000 to 20,000 years to complete one orbit. If Planet 9 exists, it would add another component to the solar system's motion, another gravitational influence affecting the orbits of all the other planets, including Earth. The effect would be tiny. Planet 9 is so far away and moves so slowly that its influence on Earth would be barely measurable. But it would be there, another thread in the complex web of gravitational interactions that govern solar system dynamics. So far, despite extensive searches, no one has found Planet 9. It might not exist at all. The orbital clustering might have some other explanation. But the possibility tantalizes, a reminder that even our own solar system might hold surprises. Then there are mysteries about the galaxy itself. We know the Milky Way has spiral arms, but we don't fully understand how they persist. Spiral arms are density waves, regions where stars temporarily bunch up. But the dynamics of how these waves form and remain stable over millions of years is still debated. Different models give different predictions, and observations don't always clearly favor one model over another. The very structure through which our solar system moves as it orbits the galactic center remains, in some ways, mysterious. We also don't know exactly how fast the Sun is moving through the galaxy. We've cited a speed of about 230 kilometers per second, but this number has uncertainty. Different methods of measurement give slightly different values, and the Sun's motion relative to different reference frames, the local stars, the galactic center, the local standard of rest, all give different answers. The differences aren't huge, but they're real, and they remind us that even seemingly basic questions like, how fast are we moving, don't have single, simple answers. Another mystery: what's the exact trajectory of the solar system through the galaxy over its lifetime? We know the current orbit, but orbits change over millions and billions of years due to gravitational interactions with giant molecular clouds, other stars, even dark matter density variations. The Sun has completed about 20 orbits of the galaxy since the solar system formed, but each orbit was slightly different. Where exactly were we 100 million years ago? Where will we be 100 million years from now? The calculations become increasingly uncertain the farther you go from the present. Some scientists have speculated about connections between the solar system's galactic motion and events on Earth. For instance, does our passage through the spiral arms, where there's more matter and more cosmic rays, affect Earth's climate or life in some way? Do gravitational interactions with giant molecular clouds disturb the Oort cloud and send comets streaming toward the inner solar system, potentially causing impacts on Earth? These ideas have been proposed, but the evidence is mixed and controversial. The connections, if they exist, are subtle and hard to prove. There's also the question of the universe's large-scale motion. We've talked about the local group's motion relative to the cosmic microwave background, about flows toward the great attractor and the Shapley supercluster. But is there structure at even larger scales? Are there motions on scales so vast that we can't yet detect them? Some cosmologists have suggested there might be flows extending across billions of light years, but the data is ambiguous. The universe might be more dynamic at the larger scales than we currently understand, or these suggestions might turn out to be artifacts of incomplete data. We're still figuring it out. And finally, there's the ultimate mystery. Why does the universe have the structure and dynamics it does? Why these particular laws of physics? Why these particular constants of nature? Why is gravity the strength it is, causing objects to move and orbit the way they do? These are questions at the boundary between physics and philosophy. Some scientists think we'll eventually find deeper principles that explain why the universe is the way it is. Others think these might be brute facts, not subject to further explanation. And still others invoke ideas like the multiverse, suggesting that perhaps the constants and laws are different in different regions of a vast cosmos, and we find ourselves in a region where they happen to permit planets, stars, galaxies, and life. These mysteries are not failures of science. They're invitations to further exploration, reminders that our understanding is always partial and provisional. Science doesn't claim to have all the answers. It claims to have a method for finding better answers, for gradually reducing uncertainty, for replacing old mysteries with new understandings that often reveal even deeper mysteries beneath. As you lie there, breathing softly, you're participating in all these mysteries. You're made of matter that includes dark matter's gravitational influence in its motion. You're part of a solar system whose long-term stability is uncertain. You're orbiting a galaxy whose structure isn't fully understood, streaming through a universe filled with dark energy we can't explain. And somehow, despite all this uncertainty, you're here, conscious, able to contemplate these very mysteries. That's perhaps the greatest mystery of all. Consciousness arising from matter, understanding emerging from atoms, wonder springing from a universe that, as far as we know, doesn't care about wonder at all. The mysteries remain. They always will. And that's okay. That's more than okay. That's perfect. Let them be. Let the unknowing sit comfortably alongside the knowing. Let curiosity coexist with contentment. You don't need to solve these mysteries tonight. You just need to rest, to breathe, to exist in this moment, moving through space in ways you can't feel, connected to everything in ways you can barely comprehend. Now gently, let's begin to bring this journey to a close. We've traveled far together, from the spin of Earth to the flow of galaxies, from the mechanics of orbits to the mysteries of dark matter. It's time to return, to circle back to where we began, to find our way home. Softly now, let's conclude. So here we are, at the end of our journey, though of course the real journey, Earth's journey through space, continues without pause. We began by talking about stillness, about the illusion of being motionless in a fixed place. And now, after exploring rotation, orbit, galactic motion, after contemplating barycenters and dark matter and the mysteries of cosmic flow, we return to that same stillness, but with new understanding. You are not still. You never have been. Every moment of your life, you've been moving at speeds that defy everyday experience, participating in cosmic dances that have been going on since before Earth existed and will continue long after you're gone. And yet here you are, feeling perfectly at rest, experiencing the gentle peace of a quiet moment. Both truths coexist. Both are real. We've learned, over these past hours together, that Earth rotates at over 1,600 kilometers per hour at the equator, giving us day and night, creating the Coriolis effect, shaping weather and oceans. We've explored how Earth orbits the Sun at 107,000 kilometers per hour, completing one circuit every 365,256 days, creating the seasons through its tilted axis, changing the night sky throughout the year. We've discovered that the Sun itself moves through the galaxy at 828,000 kilometers per hour, carrying Earth in a helical path like a thread spiraling through space. We've zoomed out further, seeing how the entire solar system dances around the barycenter, that invisible mathematical point determined by the combined mass of Sun and planets. We've contemplated the Milky Way's rotation, its journey through the local group, the vast cosmic flows that carry us toward distant structures we'll never reach. We've examined the mechanics, gravity, inertia, orbital velocity, resonance, that keep everything stable and predictable despite the immense speeds and scales involved. We've looked up at the sky and seen how Earth's motion leaves its traces there, the daily wheel of stars, the annual march of constellations, the wandering of planets, the slow procession of Earth's axis over millennia. We've reflected on what it all means, philosophically and personally, this being part of a vast, ancient, dynamic cosmos. And we've acknowledged the mysteries that remain, the dark matter and dark energy, and unanswered questions that remind us our understanding is always incomplete. Through it all, one theme has emerged again and again. Motion and stillness are not opposites. They're different perspectives on the same reality. You can be racing through space and resting peacefully at the same time. The universe is kind enough to let both be true, to hold paradoxes without needing to resolve them. Maybe that's the real lesson here, not the specific speeds or scales, important as those are, not the mechanics of orbits or the mysteries of dark matter, but the simple recognition that reality is richer, more layered, more paradoxical than everyday experience suggests. You're always more than you seem. You contain multitudes, not just in the poetic sense, but literally. You're made of atoms from dead stars. You're moving at cosmic speeds. You're participating in motions that span billions of years. And simultaneously, you're here now, in this moment, feeling still and safe and present. The ancient philosophers believed that understanding the cosmos would help us understand ourselves. They were right, but not in the way they expected. Understanding Earth's motion through space doesn't tell us how to live or what to value, but it does provide perspective. It reminds us that we're part of something vast and beautiful, that our lives unfold against a backdrop of unimaginable scale, that the ordinary and the cosmic interpenetrate constantly. Every breath you take, you're breathing atoms that have been circling the galaxy for billions of years. Every photon that enters your eye left some distant star years or centuries ago and traveled across the rotating galaxy to reach you at this exact moment. You are connected to everything, not metaphorically, but physically, through shared matter and shared motion, and the universal force of gravity that binds it all together. So, with all of this in mind, are you still awake? If you are, I hope it's not because this was too interesting, though I won't apologize if it was. The real motion of Earth through the galaxy is interesting. It deserves our attention, our wonder, our curiosity. And if exploring it has kept you awake for a few hours, at least you've learned something remarkable about your true address in the universe, about the cosmic journey you're on, whether you realize it or not. If you're drifting towards sleep, that's perfect too. Let the ideas settle like snow, gently covering the landscape of your mind. You don't need to remember the exact numbers or the specific mechanisms. Just carry with you the sense of it, the motion, the scale, the beauty of being a conscious creature on a spinning planet, orbiting a star that's sweeping through a galaxy that's streaming through space. That's enough. Before you drift off completely, I'd love to know where you're listening from and what time it is in your part of the world. Drop a comment and share your location, your time zone, your perspective on this shared cosmic journey. Are you perhaps an astronomy student contemplating these motions professionally, or someone who just finds the vastness of space strangely comforting? Let me know. The community scattered across this moving Earth is part of what makes this exploration meaningful. If you found this gentle journey into Earth's motion through the galaxy relaxing or informative, or both, please do consider giving this video a like and subscribing to Sleepy Science Student. It's a small gesture that helps me keep bringing you more calming, curious content from the world of space science and beyond. We're all traveling together through the cosmos after all. We might as well keep each other company along the way. Thank you for joining me on this journey through the real movement of Earth. Sleep well, dream deep, and may your dreams carry you to the places in space we've explored together tonight. Remember, even in your deepest sleep, you'll be traveling, spinning with Earth, orbiting the sun, sweeping through the galaxy at speeds beyond imagination. You're never truly still. You're always journeying. You're always, in the deepest sense, coming home to a place you've never left. The cosmos holds you. Gravity cradles you. The ancient motions of the universe carry you forward into tomorrow. Rest now. Let it all be. You're exactly where you're supposed to be, moving exactly as you should, part of the dance that's been going on for billions of years. Good night.